So hopefully you've got your answer, and in fact if you're doing this through Moodle, Moodle won't have let you proceed without getting the correct answer. So hopefully you know that A and B can't possibly be correct, because those expressions are not vectors, and RIP vector is certainly a vector, and so A and B can't be right. Now, A is similar to something that's going to be useful to us because the magnitude of the RIP vector, which is what we mean when we write RIP with no vector symbol on it, is given by that expression, and that will be useful to us, but it's not what the question was asking, because remember, we don't just need the magnitude of RIP, we also need one of its components. And so the answer you can just read straight off the diagram, as is so often the case with vectors. The RIP vector, which is this arrow, goes over in the x direction, a distance we've just called x, and so its x component is just x. And it goes down in the y direction, a distance that we've called yi, and so its y component is negative yi. And so then stick those together to make it into a vector with your unit vectors, and there is the RIP vector. Here is the RIP vector, and we already know we need its x component, and we can just read that off. It's nothing more than x. And we'll also need its magnitude, which is like so. And so the only thing left in this expression we need to deal with is this delta qi. Now note, looking ahead, we're going to have to integrate with respect to something. And what we will be doing is integrating over the rod. In other words, we're starting at one end of the rod and integrating to the end. Well, as we do so, the thing that's changing is y. And so we want to be able to express everything in terms of y. This little chunk will have some length that we could call delta yi. We know that the charge q is distributed over this rod. And so the charge density, the linear charge density, is q over L. And that means that the amount of charge on this little chunk, delta qi, remember what lambda is. It's a charge per unit length. And we know that the length of this chunk is delta yi, and so the charge on it must be lambda times delta yi. So now we can put all this together into our expression. We have our x component of the E field due to this chunk. Or I could simplify that a little bit. I'm going to pull things that are constant, right? Note x is constant. We're not moving our point P. So I'm going to pull things that are constant out front. There is our expression for the E field due to the ith chunk of rod. We're now ready to set up our integral. Note that the idea here is that the total x component of the E field due to the rod at the point P is approximately the sum over all these bits. Now I can take all of the constant factors out in front of the sum, and I'm only going to be summing over this part. Except that we'll never actually carry out that sum because we want the exact answer, and so we're going to convert it to an integral. So we're taking the limit as our delta yi's go to 0. In other words, as we're taking tinier and tinier little thin pieces of the rod. And so everything that has an I subscript on it is losing its I subscript because we're going from discrete chunks that we can index and count to a continuous variation over the rod. And so the expression will look inside the integral like this. delta yi becomes dyi, which is saying that we are integrating with respect, becomes just delta y. Remember, discrete things are turning into continuous things. And now we need to worry about what we are integrating over. So we are integrating with respect to y. From what to what? Well, at the bottom end of the rod, the value of y is negative L over 2. And at the top end of the rod, it's L over 2. And so we're integrating with respect to y from negative L over 2 to L over 2. And at this stage, all we have left to do is carry out this integral. We've done all the physics. I know many of you don't even know how to do integrals yet, but that actually doesn't matter, because throughout this course, I'm not really interested in seeing you do integrals. I'm much more interested in seeing you set up integrals, because that's where you're doing the physics. At the point you've got it down to an integral that you just need to evaluate, you're finished the physics, and now you're just doing some calculus. And I don't really care how you do it. So you could look it up on a table of integrals, but these days that's the old-fashioned way. The way you're more likely to do it when you come across an integral you don't know how to do is perhaps plug it into Maple, like this. Or it might be useful to know about this website called Wolfram Alpha, which will do integrals for you. So either way, you get this. And there's our final answer, except it's always good after you've done something this complicated to check the units. So notice what we have here is we have a K, which is in Newton meters squared per coulomb squared, times a lambda, which is in coulombs per meter, divided by an x, which is in meters, and then we have a length, which is in meters, over a square root of a bunch of lengths squared, so those are meters over meters, and those cancel, and I'm not going to worry about them. And so we have coulombs takes out coulombs, meters takes out a meter, and a meter takes out a meter, and we get, as we ought to, newtons per coulomb, which is correct for an E field. So you may feel that I cheated by doing the integral using Wolfram Alpha or Maple. If you feel that I cheated and you want to know how to do it yourself, I'll leave you to muddle through it. I'll give you a hint that if you do a trig substitution, this integral is reasonably easy, though you may find yourself scratching your head over how to deal with the endpoints. I will perhaps, if I have time, post a supplementary video where I just quickly show how to do that integral by hand. So this is a rather special purpose result we've got here. It applies to a rod where we are far from the rod compared to the thickness of the rod, or where the rod is very thin. And we have to be at this point P that's out perpendicular from the middle of the rod. If we look anywhere else, this expression won't apply. In particular, anywhere else, our argument that the y components cancel won't hold, and we would also have to find the y component of E. But we can get a little more mileage out of this. There's a useful further approximation. What if we have a rod and we are looking at a point that is sufficiently far away from it that we can treat the rod as thin? However, let's also say that the rod is very long. And so compared to, in particular, compared to the distance that we are looking from the rod, x, the length of the rod needs to be very large. So this is, in some sense, even more special purpose, because not only does x have to be much bigger than the thickness of the rod, x has to be much smaller than the length of the rod. But for long wires and things like this is often a reasonably good approximation. Well, in that case, we can treat the length as infinite. And so we can take the expression that we already have, and we can think of what this expression does as L gets very large. Well, in particular, as L gets very large, x squared plus L squared over 4 is going to go to, well, L is much bigger than x, and so this is just going to go to L squared over 4. And so our E field is going to go to, and that square root of L squared over 4 is just L over 2. And so the L's are going to cancel, and all we're going to get is this. And this is actually quite often a useful expression when you have a long, thin wire, then anywhere that you look that is near the wire so that its ends are far away, but not so near that you need to worry about its thickness, this will give you a good approximation to the E field. Now I'm going to do a uniformly charged thin ring. And so this is a ring which has some radius capital R, and we're looking at a point on the axis through the middle of the ring, so I've made that my z-axis, and again the ring is thin compared to the distance away, so we can treat it as having no thickness at all. Now this seems like an even more special case than the thin rod that I did earlier, and indeed it is. This is really not a case you're often interested in. However, in the next video lecture, we'll see that we can take this and turn it into something that we will find very useful, and so that's why I'm going to show it. But I'm going to show it very quickly because the process is pretty much the same as doing the thin rod. So I've already started out by writing out my delta E, and here it is fully written out. Note that we're in 3 dimensions. And we're going to have the same symmetry argument as before. For every point delta Q, there is a piece of the ring on the far side that will produce a corresponding delta E, and both the x and y components of those will cancel out. And so in fact, all we're interested in is the z component of this field. So, as before, we're going to be very interested in these components of the RIP and in the magnitude of RIP. And note that no matter what point on the ring we're looking at, there's a triangle that looks like this, which is a right angle triangle, and this side of it is R, and this side of it is Z. And so it's going to look like this, and that tells us that the Z component of RIP is just Z, and that the magnitude is just this. The next thing we have to deal with is how to write our delta Qi. We want it in terms of something we can integrate over. Well, we know that the linear density of charge on this is going to be the charge over the circumference of the circle, so that gives us this expression. And now if we think of each piece as having some little arc length, delta Si, and it's subtended by some angle that we could call delta theta I, then the charge is just the linear charge density times the arc length, and that's just this. So we can put all these pieces together and get this expression for the E field due to 1 bit of the rod. And simplifying, I can pull out everything that's a constant, which is almost everything. Note that what we're going to integrate with respect to is theta as we look at all points around the ring, and so there's only one place where theta appears. So we just put everything together in our sum, and then we let that sum go to an integral where we note that we're going to allow theta to vary from 0 to 2 pi to get all the way around the whole ring. And this now is the easiest integral in the world. So that integral just gives us a 2 pi, and then note that we have lambda 2 pi r, that's just lambda times the circumference, and that's q. And so we get this expression. I'm going to leave you to check the units, and I'm going to point something else out. And so our expression just becomes, and note that the E field drops off as distance squared, just like it would for a charge. In fact, for any distribution, this is true, that as you go to very large distances, the distances have to be large compared to the size of the object, it ends up looking just like the E field due to a charged particle again. And you can check that this is true for the expression I got for the thin rod.